Caliperness is the mathematical object which measures the total effort to straighten a multi-caliper. A caliper objects look like these things, and which has a fulcrum point, which has a left edge, which has a right edge, and the effort to straighten is defined in this way. Caliperness is the total effort of straightening multi-calipers. This effort is a tactic effort plus rotation effort plus holding effort plus sliding effort plus scaling effort plus lifting effort plus effort if any lifting and shifting is necessary plus breaking of the fulcrum effort. There are multiple types of efforts involved in straightening a multi-caliper. First of all, we have to understand what are the calipers, what are the multi-calipers, and suppose this is a caliper object and we have to think it as a multi-caliper object, then we have to place this fulcrum point at different positions and we can get a tree-like object, and these tree-like objects generate the constructions, and sometimes these tree-like objects have a rotated objects also, and these rotated objects involve into the geometry, and that forms the triangulations like these, and due to this triangulation it is a multi-caliper object. And all of these rotated calipers at the fulcrum points are rotated anti-clockwise or clockwise, and then construct the triangulations, and from those triangulation again the new branches come out, and in this way we can get the multi-caliper kind of objects. To make the things simpler, we can talk it like the share market graph, which looks like these kind of things, and where something grows down, comes down, come down, again grows, again grows, again grows, come down, again grows, get flattened or steep rise, again flattens, then come down with the different gradients. And people think it as a normal mathematics of graph, but in geometrifying trigonometry it is thought of as a multi-caliper objects, and there is an effort to straighten it. Now if it is a multi-caliper object where the fulcrum points are placed at every point of change where the graph changes, then it is a multi-caliper object, and for the multi-caliper object we need to straighten it to get the total effort necessary to get the total journey traveled in this whole process. Suppose whenever a share market comes down or goes up, whatever it is happening, then at every point the market is deciding that there is a movement, and that movement is upside down or downside up, whatever it is. Then if we measure the angle here, if we measure the total deviation occurs, is it happening clockwise or is it happening anti-clockwise, and in this way our programmers need to calculate the total effort such that we can give the instructions to the people that how to think about this kind of polylines, this kind of polygons, and these polygons we have to calculate it as a rotation effort. If the rotation effort is clockwise, then the total degree change is sometimes theta 1, and the opposite side it is 360 minus theta 1. So if this angle of rotation is theta 1, suppose this angle is theta 1, then if it is theta 1, then opposite angle is obviously 360 degree minus theta 1. That is, if this one is theta 1, then we can understand that if we have to rotate along this direction, then we have to travel theta 1 clockwise, otherwise we have to rotate anti-clockwise 360 degree minus theta 1, whichever is the smaller. is taken because no one in this world wants to do the more effort to get the same result. It is not only that, it is also shortening its size. That means the length of this edge was bigger and this one is smaller. So ultimately it has a shrinking effect, and this shrinking effect is also a effort, which is a scaling effort. Now the total effort needed for this down movement or up movement or whatever the graph is taking its shape, there is a trend movement shapes, and these shape movements are done properly as per the geometric calculations, and these are not to consider as the algorithmic complexity. We should not consider it as the computer science algorithmic complexities. We should think it as the geometric complexities to straightening the whole things sequentially. Now at the start point, where if we consider any kind of algebraic expressions or trigonometry expressions, or if we consider any kind of expression are non-commutative, then it is more syntactically strong, and then the non-commutative objects are more meaning representing things, and ambiguities reduces down. For the cases where the commutative things are allowed, then ambiguity increases. Suppose if we say that any text is written as the this is mm, this is engineering, and if we take it as a commutative, and if we say this is engineering is same as this engineering is, and that is same as is this engineering, then this syntax is non-commutative. That means the order of writing is immaterial. But is it really so? No. In any kind of syntactic system, the order of writing is always very important, because as per the rule of grammar, as per the rule of grammar, the grammar talks about the syntax, and syntax are always non-commutative. Grammar talks about grammar talks about syntax, and syntax are not commutative. So the order of writing the terms is very important. Order of writing terms is important, and if the order of writing these terms are not important, then the LR parsing or RL parsing or any kind of parsing cannot work. Parsing systems work where grammar are properly well defined and well ordered. That means for the grammar there are some noun phrase, there are some verb phrases, there are some noun phrase, and these noun phrases are there with the terminal symbols, and these noun phrases are attached with the verb phrases, and then the syntax is important, because these noun phrases always attach with some verb phrases, and those verb phrases are the actionable objects. These verb phrases connects the noun phrases differently, and then it prepares the meaning, and the parse tree systems can work, and these parse tree systems work only and only when the syntax is well ordered, and well orderliness is very important. And if we consider anything as commutative, that is reducing the power of the languages. Commutative algebraic structures are too much abstract, which hides the concrete actions. So, engineering graphic systems or the share market graphic systems always have a ambiguity because we consider things as commutative. But here in geometrifying trigonometry, we will enforce everything as the non-commutative, such that the order becomes very important. Like, suppose if we consider the 1 plus cos x plus sin x, that is different, that is different, it is different meaning from cos x plus sin x plus 1, and it has the different meaning from the sin x plus cos x, sin x plus 1 plus cos x. It has a different meaning from the sin x plus cos x, sin x plus cos x plus 1, and these all have the different meaning. There are three terms, so factorial 3 is equal to 6 types of orientations and 6 types of different meaning are there. We have to know that 1 plus cos x plus sin x, 1 plus cos x plus sin x divided by say sin x plus cos x plus 1, that generates a triangle, that generates a triangle, and this triangle say look like this. And if we take it as the sin x plus cos 1 plus cos x, and that is divided with, that is divided with say this one and this one, then it can give us a different triangle. Obviously it will get related with this, but suppose in that case the triangle is different, and obviously it can mean something different, like this. It can have the different geometry, and so we should consider that both of these are numerically one, but geometrically they are talking about the different kind of syntaxes. I will explain it thoroughly after explaining the Caliperness measures. Now here in engineering, when we are considering this, rotation is an effort and scaling is also an effort. In this way, first thing first, we have to use the hold operator, that if we are writing it as a 1 plus cos x plus sin x, then we are holding the first term, and if we are writing it as a sin x plus cos x plus 1, then we are holding sin x term. I should explain it first here. I think then it will become more interesting to explain this. I will explain this here. Suppose this one is a triangle, and when this one is a triangle, this is say, this is the pivot point, this one is the stretch point, this one is the nodal point, this one is hypotenuse, this one is perpendicular, and this one is the base, that we all know. In this way we think about the things. This one is the base. Now if this is the condition, then if this is hypotenuse and this is taken as the L equal to 1, then this one becomes, L star cos x this one becomes L star cos x base, and the seeds angle is x. Here the seeds angle is x, so the perpendicular becomes L star sin x. We got it now. Now if we write it as, suppose if we write it as 1 plus cos x plus sin x, this means L equal to 1, hold this one tightly, this means 1, and hold this tightly, hold this tightly on the space. First term is hold tightly, always we will hold the first term very tightly such that it will not move, because the whole concept is non-commutative, so the order is important. The first term is hold tightly. Now it is saying that cos x plus sin x, that means with the 1, after rotation, after straightening, this cos x will remain attached with 1, so we have to get the effect of rotating this cos x about the pivot such that it will remain attached with the 1. We will have to get this thing rotated in such a way that will remain attached with 1, because the expression is saying 1 plus cos x plus sin x, so 1 and cos x should come together, and then sin x should come after that, which will remain attached with cos x. How can we achieve that? To do that, we have to cut the point at the nodal, otherwise we cannot get this effect. To do this, we have to consider the geometry like this. We will cut at the nodal point, then we will rotate this L sin x about the stretch point, when cos x and sin x will become collinear, and after this collinearity is achieved, then sequentially we will rotate the whole bunch of line segments, like the sin x part and the cos x part together about the pivot point, such that we can straighten it and we can get the 1 plus cos x plus sin x in an order, and that order is expressed here in this expression 1 plus cos x plus sin x. Similarly, if we try to say that no, we want to write it as the cos x plus sin x plus 1, if we have to write it as a cos x plus sin x plus 1, say if the order is written like this, then obviously we are holding the cos x line segment first, and we will hold the cos x first, so we will do this like this. We will hold the cos x part first, and we will not allow this cos x to move. Now we will see that sin x is attached with cos x, and then 1 is attached with sin x. To achieve that, we have to rotate this 1 about the nodal point such that the 1 will remain attached with sin x, and to do that we have to cut the pivot point, because the pivot point cutting is necessary, otherwise we cannot rotate it, rotate the 1 about the nodal point. Here the effort of planning, the tactic effort is that since 1 comes last, since the 1 comes last, this comes last, which means we have to rotate it first. The last term is rotated first. The tactic effort is the last term is rotated first, like the stacks, last in first out. In the stack data structures we see that the last in first out, the last term is rotated first, the second last term is rotated sequentially later, and the first term is never rotated. So we have to cut at such a point where the first term will remain free from rotation. To achieve the first term free from rotation, we have to know either pivot point or stretch point are attached to cos x. Nodal point is never attached to cos x. So we have to cut either at the pivot point or at the stretch point. When we will cut the pivot point and when we are holding the cos x tightly, then only the line segment 1 is allowed to rotate about the nodal point. So the grammar works in a active construction language. Now this active construction language has the Caliperness point coming in. Now sequential rotation has a tactic model. Here cos x is held tightly, so we have to cut the pivot point and then rotating about the nodal point such that the one is attached with the sin x and one becomes collinear with sin x. So the last two terms, the 1 and sin x becomes collinear, and after this collinearity is achieved, now we are allowed to rotate the whole thing of sin x plus 1 about the stretch point to make the straightening occur. And when L cos x, that is held tight because it is the first term, and in this way the straightening is happening. And here we have seen that 1 plus cos x has a different geometry, cos x plus sin x plus 1 has a different geometry, 1 plus cos x plus sin x has a different line segment, and the cos x plus sin x plus 1 has a different line segment. Now when we form the triangulation, we can think it like this, where the common point is placed like this and a new triangle is formed, which is due to the division of this cos x plus sin x plus 1 and 1 plus cos x plus sin x. This division is creating a third triangle, and to generate this we have done some effort. This kind of effort is the geometric effort, but that is not the Caliperness effort. Caliperness effort is only up to the straightening part. This is the geometrifying trigonometry triangulation effort, triangle generation effort that occurs during the division. And the ratio effort, we can consider it as a ratio effort, and ratio effort is defined. The ratio effort is different from the Caliperness effort. I think you got it, that the ratio effort means where some bunch of line segment is on the numerator and some other bunch of line segment is numerator is a bunch of line segments, denominator is another bunch of line segments, denominator is another bunch of line segments, and the division is done, and that division is the effort used to generate the ratio. This total effort has something to say here. It says that numerator is found with a output line segment which has a particular length, and that length is a number. The denominator is also depicting some output line segment, that is also output line segment which has a particular length and that has a number. These numbers divide to give us the numerical ratio, but ultimately the numerator is a bunch of line segment which can look like this and which has different other triangulation properties also, like this kind of triangulations are commonly visible. And suppose the numerator bunch of line segment is like this, and the denominator bunch of line segment is also a bunch of line segment, that is the ball subject. And ball subjects are the superclass which has the subclasses, like line segments are also the bunch of line segments. The point is also a null bunch of line segment. um, Locked sets are also bunch of line segments. GT simplexes are also a bunch of line segments. This is a GT simplex kind of object where the pure multiplications are there and plus minus are not involved. These are the GT simplex objects. And suppose the denominator is also a bunch of line segment which has the different geometry. Say altogether it has a different geometry, but it has also output line segment, and the output line segments interact, and the initial line segments are also there. That there is a separate training videos for that. And when these bunch of line segments are interacting due to the division, the output line segments both have the output line segment. Suppose this one has the output line segment, this one also has the output line segment. Suppose this one has the output line segment, this one, uh, and this one has output line segment, say this one, and these output line segments are interacting to form the triangles as we have shown here. But sometimes due to the locked set operations, we can see that this is not possible. Suppose if you see that the numerator has the 1 plus cos x plus denominator has the sin x plus 1, then straightening is necessary. Otherwise you cannot get the output line segments to interact such that the ratio effort is found. The ratio effort is a different thing than the caliperness effort. We will focus on the caliperness of effort now, because the grammar is non-commutative in the constructive geometry. And to depict this caliperness effort, we are coming back to the straightening part only. So in the engineering purpose, while writing the programs, the syntaxes are taken the non-commutative. And even in the share market data, the first data of the calibration calculations, we take one reference trend as the first term and we will hold it tightly, and then we will take the range up to which we will do the analysis. And this range has a geometric effort. This range is, say, taken like this, and now we have a range on which we are doing to the track forward and track backward. And then within that range we are finding the total geometric effort of the straightening. And the straightening effort is very important, because the total straightening to the line segment and total journey of this straightening is actually depicting the nature of the effort the total market has done to make the alignments of the final condition from the initial condition. The initial condition is hold tight, then we will sequentially straighten the whole trend sequentially from the last in first out way. The last segment is straightened first with the next one. This is like the multi-caliper where the multiple fulcrum points are there, and at every fulcrum points we will straighten it. We will never use the stretched straightening. We will never use this kind of stretched straightening, because the stretched straightening will change the edge lengths, and every edge length has a real effort that happened due to this trend setting. So real effort, we cannot remove the real effort, so we will not stretch these. We will simply try to get the sequential rotation of the last line segment trend to align it with the next last line segment. And then at every fulcrum points we will do these efforts clockwise, anti-clockwise, and we will measure the total efforts. Say, first, to calculate these efforts, we will automatically measure the angles. Okay, so we will measure the angles first, and then we will decide the anti-clockwise rotation is going to give us a less effort, or clockwise rotation is going to give us a less effort. The least energy principle works everywhere. That is the Castigliano's theorem in the structural engineering, where not only human are lazy, but the whole nature is lazy. Nature tries to fit itself to such a position where it has to do the least effort. That is the Castigliano's theorem, and the least work principle is also applicable in the laws of nature. And if you go through the quantum mechanics also, there also you will find that least energy principle is a very important subject, and Lagrangian mechanics, Hamiltonian mechanics, and also in the Newtonian mechanics. After that, the whole analysis is done in that way. And even in the wave optics, also in the heat transfers, everywhere we have seen the least energy principle works best. And while trying to calculate the trend setting and trend calculations, the market will try to follow the least work principle. And in Sanjana's geometrifying trigonometry, the straightening method before doing any division is necessary, where we have to find the least energy principle to decide which syntax is the best syntax to write the trigonometry expression or any algebraic expression. Suppose 1 plus cos x plus sin x can have a straightening effect, cos x plus sin x plus 1 can have another straightening effect, and these effects have the efforts. And to get these efforts, whichever will give us the minimum work done necessary, that is the best way to write the syntax. Here, now after finding these angles as the theta 1, theta 2, suppose this one is the theta last, theta n, the next one is the theta n minus 1. Say here, if we have to calculate the rotation necessary here, that is the theta n minus 1, and in this way we will calculate the efforts necessary to straighten. In this way we will calculate the necessary efforts to straighten in the whole multi-caliper objects. These are the multi-caliper objects where we first measure the in this way we first get the angles necessary to rotate, and then we will decide the anti-clock rotation fits best or clock rotation fits best, and whichever is the minimum we will follow that direction. In that way we decide the Caliperness. Here the straightening is done, then this straightening is done, the sequential straightening is done. After these last two are straightened, then we will do the next straightening, and in this way ultimately we will go to the final straightening here, and the total rotation effort necessary is calculated here. For several cases we will see that this lifting and shifting are also necessary. Sometimes we will get the branches, multi branches occur in the triangulation. Sometimes we will see there are the multi branches occur, and these multi branches straightening are not so easy. To get those straightening effect, we need to break the fulcrums. Sometimes we need to do the lifting and shifting. Suppose sometimes we need to do the lifting and shifting like this, and this also carry some effort. So the lifting and shifting effort is also measured with the breaking of the fulcrum effort plus the total distance lifting and shifting necessary. The sliding is done when sometimes we see that we have to slide the branch along any edge, and that is the sliding effort, and the total length we have to cover, that we have to take care. And in this way, for several branching conditions, we have to design the whole enumerative geometry with the purpose that we have to straighten the whole thing with the minimum effort, and that minimum effort is the Caliperness. Here we have defined the total Caliperness is the total effort necessary to do the planning, that is which point to cut, which point to rotate first, and from the syntax analysis we have to calculate this Caliperness value, and after getting this Caliperness value we can find the total minimum effort a market need to do to achieve a trend, or the total minimum effort the engineering system has to achieve geometrically to get a straightening effect, such that we can do the division. And until we can do the division we cannot get the common triangle at which the two bunch of line segments interact due to the ratio. Whenever we see any ratio, obviously we have to understand that any ratio means, the ratio means some numerator is a line segment and the denominator is another line segment, and this numerator line segment is the output line segment of some bunch of line segment. The denominator is also the output line segment for the some other bunch of line segments. Both of these bunch of line segments are originated from the common single line segment L, and ultimately if no straightening is necessary, if everything are at par, suppose after doing the division, if we see after doing construction of the bunch of line segments, if we see that the output line segment and the output line segment of the numerator and the output line segment of the denominator are automatically coming end to end and collinear, end to end and collinear, then those are naturally addable. If we see they are not end to end but overlapping, exactly overlapping, then and only then we can say the division is generating 1. That means we cannot say a division where numerator divided by denominator is 1 until and unless the output line segment of the bunch of line segments of numerator and the output line segment from the bunch of line segments in the denominator both exactly overlaps on one another. We cannot say the division is generating the numerical value 1. If we consider it as a numerical value of 1, then the whole system looks chaos, because our ordinary statistics don't answer these questions, our ordinary arithmetic don't answer these questions. Only Sanjana's geometrifying trigonometry go deeper inside the total effort necessary to make the geometry aligned properly, to calculate the real trends, to calculate the real nature of the market movements. We have to understand the nature of efforts necessary to calibrate the ratios. Whenever we are calculating the ratios, we should get caution in our mind that numerical sameness is not going to tell us the real story. Real story is hidden inside the effort of straightening of the trend lines in the numerator and the efforts of straightening necessary to get the straight line segment in the denominator. Until the straightening is done, the division process will never give us the clarity about the trends. So whenever you will see the trend lines are there, get cautious that numerical statistics is never going to give you the answer until we are attacking the problems with the deep geometric nature of the movements.